Hey YouTube, welcome back to my LeetCode series. In this video we're going to solve question 287, find the duplicate number, and this is a medium question. We are going through this list of LeetCode questions that I've curated from a bunch of resources, and I'll have the link of this repo in the description below. There's a bunch of data structures for you guys to study with video lectures as well, and I also have a bunch of LeetCode questions all with amazing like and dislike ratios. So we're starting the series off in the middle of where I am with my progress of these questions, and right now we are solving question 448, find all numbers disappeared in an array. If these videos help you, please make sure to like and subscribe for more content like this. So let's get started. So we have an array nums containing n plus 1 integers, where each integer is between 1 and n. Okay. Prove that at least one duplicate number must exist. Assume there is only one duplicate number. Find the duplicate one. Okay, so I'm assuming that there's going to be a duplicate number. Assume that there is only one duplicate number. Find the duplicate one. For the first example, we return 2. In the second example, we return 3. So we have the fact that these numbers are between 1 and n inclusive. And we have, let's see here, our nums, the range of nums is between 1 and n inclusive. And our nums.length is equal to n plus 1. So ignoring these notes, these constraints for now, the brute force solution would be to iterate through all pairs and check for the duplicate. So this would loop I from 0 to n. This would loop j from I plus 1 to n. And if nums at I is equal to nums at j, then we return nums at I. Time for this is O of n squared. Space is constant. So a better solution, we'll call this solution number 2, would probably use a set. You can do this in O of n time and O of n space, where we first have a set and then we insert all nums in set. We then loop I from 0 to n, and if the set has I, then we return I. But our runtime complexity should be less than O of n squared, so that's what we have, but we have to use constant space. So the next thing that we can do, solution number 3, is with the constant amount of space now, we can have a solution O of n log n with a constant amount of space, where we sort the array first. So we sort the array first, and then we loop I from 1 to n, and if nums at I is equal to nums at I minus 1, then we return, and not I here, we return nums at I. This is what I meant. So this we return nums at I. Otherwise we continue on. Now I believe there's another solution, because we aren't using the fact that the range of the range of the solution of the input is between 1 and n. I believe we can do something like O of n with constant space if we were to use some sort of cyclic sort. But the thing is, we cannot reuse the array. It's read only. So this function is non-destructive. If the array is non-destructive, I don't see how we can have that extra information of that data structure that we've seen a number already. I don't see it at all, and I think at this point, if we can't modify the data structure and we can't have another data structure, n log n seems to be the best time. And since I'm really familiar with these type of questions, I'm going to look at the solution right away, because I know n log n would work for sure, but I don't see the solution with O of n. Wait, an idea just popped into my mind. Since the indices map to, since the values map to a specific, index, 1 3 4 2 2. This must mean, I believe there's a cycle if we follow the indices. 0 1 2 3 4 and 1 3 4 2 2. What if we travel like this? 1 2 3. This tells us to go to right here. So there's a cycle, because if we treat the array like a circular array, the values map. Well, it doesn't matter if the values were between 1 and n. If we treated the array like a circular array, we could still wrap around. But I have a feeling there has something to do with the fact that 2 maps to 4 right here, and this 2 right here as well maps to this 4 as well. Um, 1 3 4 2 2. Find the duplicate number. How can we know that at this point we've already visited 4 from the first 2? Because we visit here 1, 3, we visit 0, 1 2 3, 4 we go outside of the array, and then 2 we visit 4, and then this 2 visits 4 again, but we've already seen 4. So if we can't use any extra data structures, can we follow the pointer somehow and figure out if there's some sort of cycle? Because 2 nodes map to 1 node. The 2 nodes that have value 2 map to the node with value 4. Because if I draw a linked list, what I think happens is let's see. Basically my intuition right now is that there might be some sort of cycle created with the values mapping to indices. So I'm going to draw this with linked list to see if I can picture this better. This goes here, and then we have something like this, and then we have something like this. Oh, but they're between 1 and n inclusive. So maybe I map to the nth. So right here, I'm mapping the value to the nth, to the ith node. So this goes to 1, this goes to 3, these two go to 2, and 4 goes to the null. So there's not a cycle per se because 0, 1, 2, 3. Nothing is pointing to this node. Sorry, 3 should be, this shouldn't be happening right here. This should be pointing to this node right here. So we have bam, 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 bam. And then what's pointing to 4? 0, 1, 2, 3, 4. 4 is not pointing to the null node, it's pointing indeed to this node right here. So our list starts, I think, here, here, it goes here, it goes here. Right, so we have a cycle. This is 1, 2, 3, not 3, 3, 4, 5, and then 5 points back to 4. But I don't know if we can know that without using some sort of structure to tell that we've seen 4, and we can't modify the array itself. Okay, I'm super stuck. I'm just gonna look at the solution. At this point, I do not know where to go forwards, and I've exercised all solutions I think I have. So at this point, I think it's okay to look at the solution. So there is, of course, an O of n solution. Oh my god. Slow and fast pointer technique. Right, I just need to know if there is a cycle, and if there is a cycle, then we'll use the slow and fast pointers and they'll eventually meet up. Oh my god, I don't know why I didn't get that. So if they meet up, well, slow does not equal fast, right? So then there's guaranteed to be a duplicate. So then at that point, this is the head of the cycle detection algorithm. Then we move back one of the pointers to the head of the list and move each of them by 1 until they don't equal each other. So this is exactly like linked list cycle 2. Right, so slow equals nums at 0 and fast equals nums at 0, and then we move them twice as fast. Right, okay, let's code this up in JavaScript, and yeah, so the nums dot length is equal to 0, or it's equal to 1. I guess we're guaranteed that there is a duplicate number, so we're not going to have this. We're going to let slow equal nums at 0 and fast equal nums at 0. Or no, fast equals, yeah. And then just looking at the solution to see how they did it. Right, so while slow does not equal fast, slow is equal to nums at slow, and fast is equal to nums at fast, and then we move that one more time. Then they're equal, so we'll move slow to equal nums at 0, I believe. Oh, is it just 0? And while slow does not equal fast, we move them by 1. So this is the detection of the head of the cycle algorithm. And then we return slow. And this is O of n time, constant space, right? My question is, why does slow... I guess here we skip the head. We just go right into slow is equal to head dot next and fast equals head dot next dot next. That makes sense. So yeah, that was my thought process. I got stuck and I just simply forgot to apply the pattern of the cycle detection, head of the cycle detection algorithm, and sometimes you'll slip up like that. So if this video has helped you, please make sure to drop a like and subscribe for more content like this. I'll see you guys in the next video. Peace.